right, we'll continue here with the learning objectives. So in section 4.4, describe the relationship between volume and pressure of a fixed amount of gas at a constant temperature and express the relationship with proportionality, inequality in a graph. Well, given the initial volume, we'll do some calculations. So here we're going to look at the data, make a table, graph it, figure out the equation, which is the law, and then use the law that makes predictions based on the law. 4.6, for a fixed amount of confined gas, given the initial volume, pressure, and temperature, and the final values of any two variables, calculate the final value of the third variable. So this is, what we do is we end up with these laws, we combine those laws, and we get something called the combined gas law, which is 4.6. 4.6 is the combined gas law. I don't know why they don't just state those. State the values associated with STP. We'll talk about STP, standard temperature and pressure. All right, and then that's it for the chapter. So these are the characteristics of the gas. Gases can be compressed. Gases can be compressed because gases consist of mostly, do you know what gases consist of? It consists of mostly empty space. You know, there's particles there, but there's a lot of space in between. Is this room empty space? You say? No, this room is not empty. This room is filled with air. In fact, you know, everything's filled with air because we live under a huge blanket of air. You know, this blanket of air extends up many miles in altitude. Do you know how much this blanket of air weighs? 15 pounds per square inch of the blanket of air. And so this blanket of air, well, you know, the marshmallows know about the air. Let me just show you something here. Let's add it up. Okay, so these marshmallows are used to living in 15 pounds of atmosphere per square inch. Have you seen that?
Alright, today I'm going to be putting marshmallows in my new vacuum chamber.
It's a vacuum chamber.
Okay, so what should happen here is because there's a lot of air in marshmallows, as soon as I start sucking the air out of the chamber, the marshmallow should expand because the air pressure inside the marshmallow will make it expand. But then once all the air has been sucked out of the marshmallow, it'll just kind of stay there. But then I'm going to let the air back in the chamber, and all the marshmallows should get crushed from the weight of the atmosphere. Let's put them in my chamber and see what happens. Okay, so let's load in my marshmallows.
So they got a tower. Take a look at this vacuum chamber this person built. Do you see the acrylic? Look how thick that is. Why? Why so thick? Because, you know, 15 pounds doesn't sound like much weight, but it actually is quite a bit of weight. If this were thinly constructed, as he pulls the vacuum, it would just crush the container, you know, like a implosion.
Is it 15 pounds from all sides or just
from all sides? Because we're surrounded. It's like being underwater. You know, when you're underwater, is it just from the top? If you're, let's say, you're standing up, no, you feel it from all sides, basically. So the same thing here, it's from all sides. So this is heavy walled construction, so it doesn't collapse under the weight. 15 pounds doesn't sound much, but it can do a lot of damage. In fact, this is what we call low vacuum because he's not sucking that much air out of here, you know, because in order to get high vacuum, ultra high vacuum, this would not work. In high vacuum or ultra high vacuum, this probably would collapse, you know, the joints would break or something else would happen. And so if you need to do really high vacuum work, that kind of acrylic is not good. Instead, use things like stainless steel or Monel type apparatus. This is probably Monel here. This very thick wall, like half-inch thick wall, steel type structures, you know, with submarine-like windows, so it doesn't all implode. Because, you know, 15 pounds doesn't sound like much, but if you suck all the air out of here, you know, then all of a sudden you don't have that weight inside. There's an imbalance of weights which can cause it to implode. You need the weights balanced. And if they aren't, then you gotta make sure it's mechanically sound. Here. And so this is ultra high vacuum. In fact, there are ratings for vacuum. You know, there's ultra high vacuum. Actually, you know what a perfect vacuum is? Have you ever heard of a perfect vacuum? A perfect vacuum is empty space. There's absolutely nothing in there. So, totally empty. But it's very hard to get a perfect. In fact, nobody's ever achieved a perfect vacuum on Earth because it's too hard to suck everything out. So, ultra high vacuum, medium vacuum, low vacuum. That marshmallow chamber is a low vacuum. Here.
Marshmallows loaded in. Let's turn on the vacuum pump and see what happens. Okay, the pressure's decreasing in there. Let's see if it looks like they're getting a bit bigger. Oh yeah, they're starting to get bigger.
This is just lifting the weight off the marshmallows.
There they go.
But they're like balloons.
Oh, how big they're getting. Did they fill up the whole chamber?
It did fill up the whole chamber, but like balloons, they might pop.
That's as big as they got, so now the air has gotten out of them. So what's happened is they equilibrated with the vacuum, so now there's a vacuum inside the marshmallows. They stopped expanding. Okay, now we got a low vacuum in our marshmallows. Very low air pressure. Okay, now I'm going to open the air valve and let in some air pressure. See what happens to our marshmallows. Whoa, those just shrunk. Look at that. Look at the marshmallows. Okay, let's figure it out. Oh, that's cool. Okay, so here's our marshmallows. We made marshmallow raisins.
Okay. So gases can be compressed or expanded because gases consist of a lot of empty space. Gases have low densities. Do you know about what the density of a gas is compared to water? Water has a density of about 1 gram per milliliter. Gases have a density of about what? Would you say 1,000 times less, 100,000 times less, 1,000,000 times less, 1,000,000,000 times less, 1,000,000,000,000 times less? What makes most sense? Gases are less dense. How much less dense? Well, I mentioned this briefly when we looked at the slide of densities, but it's about 1,000 times less. And so if it's about 1 gram per milliliter for water, then for gas it's going to be about 1 milligram per milliliter. Or 1 gram per liter rather than 1 gram per milliliter. And so it's about 1,000 times less. In fact, air, I mentioned air has a density of about 1.3 grams per liter or 1.3 milligrams per milliliter. Gases may be mixed in a fixed volume, so liquids can't be mixed in a fixed volume. You know, the volume would increase if you mix 2 liquids. Gases exert a constant pressure against the walls. that's going to be uniform. So that was the earlier question about gases. And so here's how we can visualize that. So gases can be compressed. So if there are two masses, but three masses compresses the gas. What that means at the particulate level, this is kinetic molecular theory here, the particulate level, we just have less empty space. So this is going to be more crowded, this is less crowded. If we remove masses, then we can expand out. Eventually, what would happen if I remove this mass here? What do you think would happen? What would happen is, if I remove this mass, then the lid would raise up here until I get 15 pounds per square inch pressure here, which matches the 15 pounds per square inch outside. And so there's 15 pounds pushing up here, and then once I had 15 pounds pushing down, then the lid will stop moving. And so if I remove this mass, the lid will rise until it stops. And that's where it equilibrates. Okay, guys, it equilibrates with inside and outside here. Now pressure, the way we think about 15 pounds, it's not like, you think about these atoms seem weightless, don't they? The atoms seem weightless because they're floating around in there. So what is pressure? Pressure is a result of the collisions. You know, these atoms are floating around, yes, but they're going to slam into the walls. As they slam into the walls, they cause force, and that force is what we term pressure. And so the pressure is due to collisions of the gas particles with the walls. Now, the more collisions we have, the higher the pressure. So here, the more collisions, higher the pressure. More collisions per square inch. The fewer collisions, the lower the pressure. So lower pressure here per square inch. This is what we call a vacuum. Technically, what a vacuum is the pressure lower than ambient pressure. So if the ambient pressure outside here is 15 pounds, so there's 15 pounds pushing here, and there's 15 pounds pushing up, what we can do is we can pull up the lid. If we pull up the lid, that's going to expand this and lower the pressure even more. So we create a vacuum. We create some kind of suction here, which makes the pressure inside here lower than the pressure outside here. Outside, there are a whole bunch of air molecules or air particles outside causing collisions. They don't show the air outside. That would be the pressure. Here's a comparison of gas, liquid, solid. The solid is the iron nail. Does iron consist of molecules of iron or atoms of iron? Is this a molecule nail? Nail consists of molecules like atoms. No, they're atoms. You know what kind of lattice this is? I talked about covalent lattices. Do you remember that? Ionic lattices. I didn't really explain that. We'll talk about it later on. This is called a metallic lattice. It's metal atoms. Then we have liquid water, and then we have the gas. These are molecules for sure. So this is not helium. Does helium form molecules? Helium does not form molecules. This is probably something like oxygen, which forms O2, or nitrogen, which forms N2. Usually, you know what blue is reserved for? Blue, the color is reserved for nitrogen, so I'm guessing this is nitrogen inside this blue. Red is usually reserved for oxygen, and white is reserved for hydrogen. Green for many different things. Green, but most of the time it's chlorine. This is not chlorine. This is iron. But when you look at this, the molecules are spread apart. They're moving. These molecules are moving too, but they're close together. In fact, liquids and solids are not compressible because why? Well, this is kind of a fixed volume too. I mean, you can put gases into a fixed volume. Liquids and solids are not compressible, not because of a fixed volume or anything like that. They're not compressible because there's no room. I mean, this is already crowded. And if you try to squeeze them closer together, they're already touching each other. If they're already touching each other, can they squeeze in that much closer together? So you can compress it a little bit, but not much. Here we can compress it because they aren't touching. There's a lot of empty space. Here we can't compress it either because the atoms are touching. And so liquids and solids aren't compressible because they're touching one another already. But gases, no problem. In fact, Here, if I have the red gas, I can add some green gas to this in the same volume because there's empty space here. The pressure is going to go up, but I can just force some green gas in here and keep the same volume. Could I do that with water? Let's say what I want to do is, if I'm backpacking or something like that, I don't want to carry big bulky water. So what I'm going to take is 1 liter of water and 1 liter of water and compress it down to 1 liter. So 2 liters of water compressed into 1 liter. Is it possible? No, because the molecules are touching one another. It's impossible. So, but you could do it with the gas. You could take 1 liter of red gas, 1 liter of green gas, and compress it into 1 liter gas mixture. And that's not a problem. Gases exert uniform pressure in the container. So the top and the bottom are the same pressure. However, liquids do not. Liquid, the top of the liquid is going to weigh less than the bottom of the liquid. It's like in a swimming pool. If you're 9 feet under, you have all the weight of the water on top of you. It's going to generate high pressure. But if you're near the surface, you have a lot less water, a lot less weight on you. Weight is the same thing as pressure. Weight is a force. All right, I'm going to stop a little bit early here because we're going to have just a little assessment quiz. These quizzes aren't worth that. These quizzes are just worth a point. So don't stress out about this. I just want to see where people are at in terms of dimensional analysis. And so what we're going to do is we're going to do this problem. Let me just tell everybody the problem first. We are going to do number 69. Here. So can you do it on this index card? I'm going to pass it out. If you get stuck, just try to take one step at a time. But if you do get stuck, just try to show as much work as possible because I think you get partial credit. The more steps, the better. The reason I do this is because even though we did this is the exact same problem we did before, right? This is the exact same problem I did before, but it's like this. I want to learn how to play the violin, and so I'll just watch YouTubes. I'll watch a YouTube of a really good violin player. Will I be able to pick up the violin like that, just watching? No, and the same thing with this. You know how many times I've done problem number 69? Hundreds of times. Hundreds of times. So it's easy for me, right? And so if you watch somebody that it's easy for, it's always tricky. And so it's like this. My analogy is this. Let's say you're on a jungle tour. And so you're on a jungle tour, you're going through this unfamiliar jungle, and you have a guide. And so the guide says, okay, just follow me. And the guide winds his way through, or her way through the jungle. And so the next day, the guide's sick. The guide's absent. And so you have to go through the jungle by yourself. And then you start noticing forks that you didn't notice before. Oh, there's a fork here. Should I go left or should I go right? Those forks you don't pay attention to when you have a guide because the guide will just tell you which way to go. You don't have to think about it. And so the same thing happens when you're watching somebody solve a problem. You don't see all the forks. That guide might have made the same mistakes you're going to make. They might have picked the wrong fork. You don't know until you try yourself. So what I want to see is I just want to see where or if people are getting to the destination or they're taking the wrong fork. I just want to see. And so give it a shot. If you remember the answer, I need to see the work too. You might just remember the answer. But you have to show the steps. how you get to that answer.